Assalamualaikum and good days everyone. This is my group assignment, which is the topic that we chosen is exploring Cooper pairs, the foundation of superconductivity. This is my group member. The introduction. Overview. Our knowledge of condensed matter physics was completely transformed by the intriguing phenomena known as superconductivity, which was discovered in 1911. When cooled below a critical temperature, it is typified by the expulsion of magnetic fields and the total elimination of electrical resistance in some materials. The produce of Cooper pairs, which was initially described by John Bardeen, Leon Cooper, and Robert Schirfer in 1957 using the BCS theory. Then, two electrons can form a bonded state despite their inherent repulsion when they form Cooper pairs. And then the fundamental processes of Cooper pair generation and its crucial function in superconductivity are examined in this assignment. The formation of Cooper pairs. Firstly is lattice-electron interaction. An area of elevated positive charge is produced when electron passing through a crystal lattice slightly distort the lattice. Secondly, repulsion is overcome by effective attraction. The two electron inherent Coulomb resistance is overcome by an effective attractive force created by their interaction via lattice vibration or phonons. Thirdly is electron pairs that are bound. A linked quantum state with position opposing spins and momentum is called electron pair. Is created by this pair. Lastly is gap in energy. The superconducting state and the normal state are separated by an energy gap. So this is the diagram of formation of Cooper pairs. Next is role of Cooper pairs in superconductivity. Firstly is collective quantum state. Cooper pairs form a microscopic quantum state where all pairs behave coherently. Secondly, zero electrical resistance. The Cooper pairs move through the lattice without scattering. Thirdly is Meissner effect. The presence of Cooper pairs expels magnetic field from the superconductor. Fourthly is stability against thermal fluctuation. The energy gap protects the Cooper pairs from being distracted by thermal energy. Lastly is quantum coherence. The pair electrons maintain phase coherence, which is essential for the superconducting properties.
Next, I will be presenting on the BCS theory of superconductivity, a revolutionary framework developed in 1957 by John Bardeen, Leon Cooper, and Robert Schirfer. This theory explains the phenomenon of superconductivity, where certain materials exhibit zero electrical resistance below a critical temperature. For their groundbreaking work, they were awarded the Nobel Prize in Physics in 1972. In this presentation, we will explore its key principle, mechanism, and applications. Let's begin with the key principle of the BCS theory. First is electron pairing Cooper pair. In superconductor, electron near Fermi level form pair due to their interaction with the crystal lattice. This pairing is mediated by lattice vibration, also known as phonon, which create an attractive interaction between electrons. Second is the energy gap formation. Cooper pair exists in a lower energy state, forming an energy gap of approximately 0.001 above them. This energy gap prevents collision that would normally lead to resistance, ensuring zero electrical resistance. Third is zero resistivity condition. Superconductivity occurs when the thermal energy is less than the energy gap. Under this condition, Cooper pair move collectively, enabling resistance-free current flow. Now, let's look at the mechanism of superconductivity. First is lattice distortion. As a moving electron passes through the lattice, it polarizes the surrounding atom, creating a temporary region of positive charge. A second electron is attracted to this region, forming a Cooper pair. Second is the phonon exchange. Virtual phonon, which are quanta of lattice vibration, mediate the attraction between the electron, overcoming their natural repulsion. Third is quantum behavior. Copper pair condense into a single quantum state, behaving collectively as a boson and following Bose-Einstein statistic. The mathematical foundation of the BCS theory can be summarized as follows. First is critical temperature. The critical temperature below which superconductivity occurs is expressed as Tc appropriate to the exponential to the power of -1 over n0v, where n0 represents the density of state at the Fermi level and is the strength of the electron-phonon coupling. Second is energy gap. The energy gap is temperature dependent and vanishes at the critical temperature. At absolute zero, the energy gap is equal to 1.75 Boltzmann constant, critical temperature, where the Kb is the Boltzmann constant. Finally, let's explore the consequences and the application of the BCS theory. For the consequences, first is isotope effect. The critical temperature is inversely proportional to the square root of the atomic mass. This confirms the dependence of superconductivity on lattice vibrations. Second is limit of superconductivity. High temperature, strong magnetic field or excessive current can disrupt copper pair, destroying superconductivity. The third is energy and current properties. Uniform energy gap in the presence of magnetic field. Quantization of magnetic flux in unit of 2e per h. The application, the first one is Josephson effect. This phenomenon involves the tunneling of electron pair, copper pair, through thin insulating barrier, producing a supercurrent. It is like the basis for devices like squids, which measure magnetic field with extreme precision. Second is high temperature superconductor. This material deviate from BCS theory but exhibit superconductivity at much higher temperatures, often in ceramics compound.
So, next for application, we have a few of application. For the first one is quantum computing. Quantum computing is over pair over superconducting qubit, which is the building block of quantum computer, and then their ability to maintain coherency to faster energy exchange computation. And then for visual one is diagram of quantum circuit or superconducting qubit, which is mentioned real world example like IBM and Google's. And then for the second one is magnetic levitation. So this is the result. This result is frictionless, high speed, and transmutation, which is visual one is emission of a levitation train. For example, of STM 3233. So this is the example for the diagram of magnetic levitation. And then for the third one is medical imaging, which is MRI. This explains about superconducting magnet MRI, which use copper pair to generate strong, which is stable magnetic field, and then this ensure clear imaging without energy loss. And then for visual one, MRI machines in action, which is highlighted several important health steps. So this is the picture of MRI medical imaging that used in hospital for modern hospital. So the fourth one is energy application. Energy application is explained about superconducting cable powered by copper pair ensure zero energy loss during electricity transmission, which is copper pair are also key in energy store system like SMES and fusion reactors. For visual diagram of a superconducting power cable and then illustration of fusion reactor like IPL. So for the next application is particle physics and accelerator. So in high field magnet, which is superconducting magnetic accelerator like the Large Hadron Collider (LHC), depend on the zero resistance properties provided by Cooper pairs, and it's used to steer and accelerate particle for cutting edge research. And then for the fusion energy research, magnet computing is used for superconducting fusion rate is used to prepare current to generate stable magnetic field, and it helps in plasma containment for nuclear fusion experiment. So this is the picture for magnetic computing that use in fusion energy research. So the next one is advanced energy technology. So for advanced energy technology, it's used for SQUID, which is superconducting quantum interference device, which is exploit computer track for highly sensitive magnetic field detection, and then for application, it used for brain monitoring, which is we can look at the picture. So this is the application for brain monitoring. So for the final one is fundamental research and material science. So in fundamental research and material science, we use for high temperature superconductivity, which is exploring Kuiper pairs, help identify material that exhibits superconductivity at high temperature, which is potential to revolution energy system with room temperature superconductivity. So this is a few of the applications that use the pairs.
Superconductivity has revolutionized the way we understand the harness electricity. One of the most groundbreaking advancements in this field is high-temperature superconductivity, or HTS. What is high-temperature superconductivity? High-temperature superconductors, also known as HTS materials, belong to a family of substances characterized by Cooper oxide planes, often called cuprate superconductors. These remarkable materials can operate at temperature above the boiling point of liquid nitrogen, making them the champions of transition temperature among superconductors. Their ability to work with liquid nitrogen as a coolant has significantly broadened their real-world application, providing a more practical and cost-effective solutions. HTS materials offer a range of benefits over their low temperature counterparts, like lower cooling costs due to their compatibility with liquid nitrogen, compact and lightweight systems enabled by their high currency density, and enhanced stability in magnetic levitation and field application, unlocking new possibilities in technology and transportation.